So the final chapter of today, and actually of this course, is going to be about high-dimensional data. And what I mean by high-dimensional is data that contains a very large number of variables compared to the number of observations. So in economic research, we usually encounter data where the number of observations is much larger than the number of explanatory variables. However, in practical applications or in other fields, the number of explanatory variables might vastly outnumber the number of observations we can get. So think about genetic data to explain health outcomes. There's like way more genetic expressions or genes than you can ever create a reasonable sample. Also, if you're trying to, for example, classify shoppers by their Google search queries, there's all these possible combination of words that people might Google, and these vastly outnumber the number of people that you can ever sample. In addition, for example, think about health markers that explain mortality. There's like blood pressure, different components of your blood, obesity, and so on. Like there's a huge number of potential explanatory variables compared to the number of people you can survey. So why is this a problem? Well, to understand why having many more explanatory variables than observations is a problem, it really helps to think about OLS in terms of solving a system of equation. And if you remember in your linear algebra class, you probably wrote a system of equation as ax equals b. Well, solving OLS is very similar. It's essentially also x times beta equals y, which is a system of linear equations. Usually, however, number of equations n is much larger than the number of coefficients, which we call p. So the system is determined. We have more equations than we have unknowns. The problem then is, of course, that x is not invertible, so we cannot solve this system by simply inverting x. However, if x has full rank, which means that all the variables are linearly independent, we can pre-multiply this system of equation by x prime, and x prime x is invertible if it has full rank, so we can then pre-multiply from the left by the inverse of x prime x, and this leaves us with the familiar expression for beta, which is x prime x inverse times x prime y. So OLS kind of solves the system of equation by technically projecting the observations into the column space of x, and more intuitively it means that it's kind of pushing all the y observations to the closest point where they are a linear combination of the explanatory variables. However, what happens if p gets very large? So if we're approaching a point where we have the same number of variables as we have observations. Well, if they're exactly equal, then, and as long as they're linearly independent, we can simply solve the system x beta equals y, because now x is a square matrix with full rank, so we can invert it, and we can simply solve for each beta. However, if the number of explanatory variables is larger than the number of observations, we have more unknowns than we have equations, and therefore it's not possible to solve this system of equation. Also, if you're just approaching the number of observations, or if p gets very large, even though you still have fewer variables than you have observations, you might still run into problems with multicollinearity, because simply if you have a very large number of variables, there's a large chance that one of them is a linear combination of the others, and therefore you don't have full rank in your X matrix anymore. And this is especially problematic when you're using computers, because computers have limited precision. So even though they're technically not linearly dependent, the limited precision of your computer might just think that, well, these two variables or these several variables are so close to each other that they might as well just be linearly dependent. So what we need to have is kind of a way of reducing the dimensions. And there are several ways of reducing dimensions, and the one we're going to talk about today is the shrinkage methods. And shrinkage methods are one way of kind of selecting only the relevant variables from a very large set of potential covariates. So we will talk about LASSO, and LASSO stands for least absolute shrinkage and selection operator. And the idea behind LASSO is that even though we know that OLS is an unbiased estimator, we might fare better if we accept a small bias, but instead reduce the variance a lot. And this is kind of the main idea, because even though OLS is unbiased, it might have a very high variance in the coefficient estimates, because when you're using a lot of explanatory variables, you're using up a lot of the degrees of freedom. So what LASSO does is it basically OLS with constraints. So we minimize the same squared deviation as before. So we calculate y minus x prime beta, where x prime beta is simply the predicted value. And we minimize this, but in addition, we now have this constraint that the sum of all of our coefficients should be smaller than a pre-specified value. We can rewrite this using the Lagrange method, and then minimize the function where we minimize the squared deviations plus lambda times the sum of all beta coefficients. And now we have this lambda parameter, which determines how strong this constraint should be. So if lambda is very large, this means that our estimates need to be very small. So we will restrict the number of covariates that are acceptable by a lot. However, if lambda is 0, then this is simply OLS, and we have like an unconstrained optimization, and we can just get the same coefficients that ordinary least squares would give us. And since LASSO uses the absolute value of the beta coefficients, it will reduce the coefficients that are thought to be uninformative to 0. This means that LASSO also serves as a selector. It's not just reducing the estimates, but rather what it does is everything that is uninformative will just be completely reduced to 0. Alternatively, you can restrict the sum of the squared betas. So think here, instead of the absolute value, you say that the square needs to be below a certain value. And what this does is it does not set some of them fully to 0, but it rather just reduces all of them a lot. So it does not serve as a selection method. And this is why LASSO is kind of very elegant, because it automatically selects only the relevant variable for you. The last one is kind of the elastic net regression, which is essentially just a linear combination of these two norms, where we just say that it should both reduce the squared deviation, but also the absolute deviation, and give a convex combination of the two as a constraint. So for the rest of this, we're going to look at LASSO only, because it has this very nice feature of selecting a model. So let's look at an example. We have data on credit balance for a bunch of the bunch of customers, and we would like to explain their credit balance by using some observable characteristics of these customers. And this is a classic example where if you have a small sample, there might be a lot of observable characteristics, and we want to use LASSO to just tell us like which of these are informative, and everything that is not informative, it should not estimate a noisy coefficient, it should just reduce this coefficient to 0. So here we can see that if you just regress the balance on all available covariates, here we have 14 covariates. This gives us like very noisy estimates because we have a rather small sample. In R, we can implement LASSO quite efficiently using the glmnet function. And it's written by Robert Tipshivani, who was the inventor of LASSO, so can be confident that this actually works as intended. And so what this does is glmnet just runs a regression with a constraint on the coefficient, and then you can specify whether you want this constraint to be the absolute value, so it should be a LASSO, or the squared value, so it should be a ridge, or a combination of these two. You need to also give glmnet some additional parameters. You need to type what family you want the regression to be. Here we're going to use Gaussian, and Gaussian stands for just OLS, whereas other options are if you, for example, have something with limited dependent variables where you either run like a probit regression or a Poisson regression. The alpha stands for the mixture of the norm. So again, alpha equals 1 will give you LASSO, alpha equals 0 will give you ridge, and anything in between gives an elastic net regression. And then lambda is the lambda that we have looked at here, which tells us how much do we want to restrict the coefficients. Also keep in mind that the function is not very flexible when it comes to data types, so you need to actually code everything as a numeric matrix and feed this into the function. The function does not know how to deal with like data frames and tables and so on. So that's one of the drawbacks of this function. So let's take an example. I create the matrix. So I took the balance out of the data to create the explanatory variables only. And then I feed in the explanatory variables as the x, the balance as the y variable. I specify I want to have a Gaussian regression. It should be LASSO. And we set the lambda equal to 60. And this is just an arbitrary number that in this case fits well. So generally there's no like fixed rule for what is the optimal lambda, but rather you have to, this is one of the parameters that you have to figure out by using cross-validation. So in this case here, if we set lambda equal to 60, it will just give us 5 explanatory variables with non-zero coefficients, and all the other variables will be set to 0 because they're not informative. And since LASSO has this constraint that the sum of the absolute values of the coefficient cannot be above a certain value, it needs to make as many coefficients equal to 0 as possible in order to fulfill this constraint. So yes, so we see that these 5 coefficients here are probably going to be the most informative, and we see that income, the card limit that you have, the number of cards, and whether or not you're a student are the most informative explanatory variables of the credit balance of a customer. And I think this also, it makes intuitively sense that income and the limit that you have explain a lot, like how much you use your credit card actually. Also, whether or not you're a student, because then probably means that you don't have income, so you're heavily relying on your credit card. So the thing is that LASSO takes away the problem of selecting a model. However, it's not a completely automated approach, because there's still the question of how much should we actually restrict our coefficients, and therefore what value of lambda should we choose. So if we just purely after prediction accuracy, we can simply use cross-validation for this. Instead of using cross-validation to compare models with different covariates, we can use cross-validation to compare models with different values of lambda. And we could use, of course, the tidyverse, but luckily the GLM-net package has a built-in function to cross-validate LASSO for a wide range of lambda values. And we can also specify the number of folds that we want to have, which then determines how oftentimes the dataset is split into training and validation datasets. To do this, we use the function cv.glmnet. We again set alpha equal to 1, number of folds to 10. And then after we run this, we can just take the lambda from the output as lambda that minimizes the prediction error. And here it gives us an optimal lambda of 5, which is much lower than the 60 that I've used previously. And since this is much lower, it also means that the optimal model is way less restricted than the one I previously built. So but keep in mind that this only goes after prediction accuracy, and kind of tries to avoid overfitting, but still give you a good fit on the testing data set. So now that when we use the best lambda, which is around 5, you can see that the optimal model here now contains 8 explanatory variables as opposed to the 5 that I had previously. So it is a little bit more complex, and it also involves a variable for h squared, and it contains a interaction between education and gender.